So let's talk about particle size. Okay. Is that okay? You guys ready? So okay, and again I know particle, talking about particle size, and lunch will be difficult, right? So when you eat lunch, make sure to notice what type of different particle sizes that you're eating. Okay. So what variation in particle size that you can observe. Okay. So particle size is very important, right? So for any process development, process streams, particle size characterization is important. Again, unfortunately, we are not dealing with well-defined shapes, right? So for example, if you're talking about spherical particles, cylinder, cuboid, etc., those are well-defined shape, right? So you just need one number to tell the size of that material, right? For example, spherical particle, if you know the radius, then you know the sphere, right? If it's a cylinder, maybe you need two dimensions, length and the height and the radius, right? So you have the cylinder dimensions, very uniform, very regular particle, right? Cuboid, if you know the side length, then you know the the size of the material, right? But unfortunately, in ag systems, we are not dealing with regular shapes, right? So you take any kind of agricultural materials, they are never regular shape or regular size, right? Take anything, soil, from soil till any product, their sizes are completely different. We always get a distribution, right? And their shapes are also not uniform. That makes it very complicated to characterize the size, right? So again, just an example of kernel here. It's X-ray tomography image of a corn kernel. So I put that in. We use this X-ray CT scanned images to develop corn kernels when we simulate using DEM modeling. So for get the accurate sizes, okay, and shape. So what are some of these size characterization measurement systems that you can think of? Any examples of size measurement techniques? Malvern. Laser diffraction, yes, that's very common now, right? Most of the labs will have, most of the industry uses. Okay. Any other systems that you can think of? Sieve analysis, very common, right? So that's the most go-to place for size measurement, right? So what are the techniques that you can think? Okay, scanning, exactly. So microscopy technique, it could be scanning electron, optical, any type of microscopy technique, right? Anything else? What's size exclusion? Okay, see, it's again very similar to micro CT, and what is that? It comes in between the, what technique is that? So suddenly went blank. Okay, so very very similar to optical and right, optical method, right? Very close to optical method, right? SEC technique. Okay, well I think I have a slide on that. Okay, any other technique? What? Okay, confocal laser, using laser, again it's a light principle, right? Anything else? I think you almost covered most of the techniques, most common techniques. Okay, so how do we measure size? I don't know, you might, many of you would have seen this slide, right? So how do we measure size? Again, this is from Malvern. Okay, so what do we do is, for, and it's said, for any agricultural material or food material, the sizes are not uniform, and then the shapes makes it complicated, right, for measuring the sizes, right? So what do we do is, you take that material and compare with another property, okay, just to make it as a spherical particle or spherical material. Okay, so spherical, again, why we are making it into a sphere? So we just can define using one number for that particle, size using one number. But for that, getting that spherical size, either again we compare with the sphere of same weight, same mass, same sieve aperture, maximum length, minimum length, surface area, volume, etc., right? So for one same particle, how many different sizes you can measure, you can see, right? So the sizes change or sizes differ, right? So depending on the technique that you use, the size is also not the same, right? So it told SEC or sieve analysis or laser diffraction, right? So the sizes that you measure from these techniques will not be the same, right? So why it's not the same? Because we are using the fundamental principle, a different fundamental principle or different fundamental property to get the size of that material. Okay. So that's again somewhere in the slides I should have that. So when you measure size, make sure you do not compare sizes measured using two different instruments. So you are not comparing apples to apples. If you are comparing with using two different measurements, then the physics that we use to measure is completely different and the sizes are not the same. Okay. So same, the size is also same and also their distribution will also be different. Okay. We will talk about distributions in later part of the class. Okay. But most importantly, what do we how do we characterize size is we correlate with the end purpose, end use. Okay. So why do we characterize or why do we measure the size for? Okay. Just as an example, if pneumatic conveying, if you are measuring some size for pneumatic conveying, then again we use the Stokes principle or aerodynamic diameter of the particle when you use for pneumatic calculations or pneumatic systems design calculations. Okay. At the same time, if you are calculating the size of a paint particle, for paints and surface paints, okay, then you wanted to use based on the surface area diameter. Okay. So how much surface area that particle can cover when you are painting. Okay. Same for coating too. If you are coating particle to particle coating, so then you will have to worry about the surface area of the surface area dependent size of the particle. Okay. So you will use the sphere of same surface area to the sphere of your particle and then get the size of that particle. Okay. So we can go on theory for lots of many things, but finally what it comes to is what type of instrument you have in the lab. Okay. If you do not have a laser diffraction, what we do is end up with sieve analysis, right? That's a common, it's not expensive. Just use a stack of sieves and get the the size of the material, right? But now right, you should not use the same sieves for same size for other purposes, right? So when you are measuring, make sure you are measuring the accurate size for the purpose that you wanted to use. Okay. So same, if you are dissolution, mostly again surface area, depending on again the purpose, you will have to use the appropriate size measure. Okay. So again, before going to example, again, went through most of these, size measurement techniques. Should see. I'm seeing the, trying to see the method that you mentioned, SEC. See it here, but I have it somewhere. I forgot the exact physics principle that they use in SEC, but okay. So again, size measured using different principles. Again, we'll have different measures, so don't compare when you are measuring sizes measured using two different instruments. Again, most often we use the size to monitor the process change. Okay. So how the size is changing due to some milling process. I will come back to that in an example, with an example in a minute. And again, in many places, sizes are correlated with the property that we wanted to measure. Okay. So I'll come back to the size measurements on relative. For example, going back to wheat flour milling example. Okay. So what is the size that we talked about? What is the minimum particle size for wheat flour? Yeah, you all have a good memory than me. Okay, 140 microns, right? So that's what when you are measuring the particle size of wheat flour. Okay, So we in general, talk about whether the particles are, around that 140 micron range, right? So if it's above or below, we don't care, we don't, quantify that accurately if it's above or below. If it's closer, then again, okay, we use that measure, okay. For again, size is measured and correlated with other, properties. Most often when it comes to, downstream processing use, we, try to correlate with their, size and their, behavior, Dissolution, in you all, most of you at least would have used fruit powders, right, for making, drinks and stuff. So then again, you wanted, smaller size powders, right, with high surface area per unit gram or per unit, volume, so that they dissolve immediately, right. Same thing, again for, going back to wheat flour example too, we talked about ash, right, ash and its effect on baking quality. So if you wanted to have, if you have ash also, their particle size should be very small, right. If it's very larger in size, then again that will affect its baking, properties, okay. So again, depending on the downstream process, you worry or you care about the type of, measure, measurement method, or how accurately you wanted to quantify the, size, okay. So I'll go through some examples, okay. So why size is important, okay. So one is, when it comes to mixing, okay, as the picture shows here, okay. So when you reduce the size of the particle, again when it comes to mixing and blending, you might get a better uniformity in mixing, okay, than in a larger size, okay. So if you have a larger sized particle, you can see the relative standard deviation of mixing will be high, but if it's small size powder, then your mixing quality might be a little better. Your relative standard deviation will be very low, okay. Will influence blending or mixing, okay. And then again on flow behavior, right, so how it affects flow. So which particle will flow better, small particles or large particles? Small particles, okay. So one more option, large particles, okay. You can go wrong only once, right, small or large, okay. So usually the larger particles will have a better flow in general, again it's not, it's not, true all the time, but in general, will have, the cohesive surface forces will be low when it comes to large particles, and then many of the larger particles will have a, again, inertial force that is high. Okay. So if you have high inertial force and less, cohesive surface force, then the flow behavior will be better, okay. So again, I'm not going to do this, but we will talk about bond number, later, little later, okay. So again, bond number, you would have learned about bond number, right? So gives a ratio of, at least except the agriculture students, maybe ag engineering students, you would have learned. So it's a ratio of surface force to inertial force, okay. So as the bond number increases, the cohesive surface forces becomes relatively more important, okay. That means if the cohesive forces are high, then the flow will be challenging, flow will be difficult. So if the particles are larger, then the cohesive forces will be low, and then they flow better, okay. And just one other quick example here, some of you know Hausner ratio, flow function, etc., right. So these, again, we'll talk about these when we talk about powder flow, but just giving a quick, background. Hausner ratio gives some indication of powder flow behavior. So with increase in particle size, the flowability goes up, or the flow behavior goes, becomes better. Same thing, flow function will also improve if the particle size goes up, okay. Any of you measured flow properties using shear cells or any other instruments? No? Okay, so again, oops, what did I do? Okay. So dissolution time, we talked about, dissolution time, right? So you all know about, most of you at least know about Fick's law, right? So Fick's law, again, that, characterizes the dissolution rate, and again you can see it mostly dependent on the surface area, right? So surface area that comes from the radius of the particle. Okay. So again, if the radius of particle is smaller, okay, the surface area per unit volume is higher, then the dissolution rate will also be higher. Okay. This might be little difficult for you to see, but again, these graphs shows the dissolution behavior of different powders from starting from large particle size, and the lines on the top are smaller particle sizes. Okay. So you can see the nutrient release or drug release is very high or quicker for particles of smaller size. Okay. For larger particles, the nutrient release is much slower. Okay. So how does it affect your particle design or granular material design? For example, you would have learned, what is that tablet name? Yeah, Gelusil. It's called Tums in the US. How many of you would have used Gelusil, right? It's a tablet for if your tummy, stomach ache, if you ate more, if you have acidity problem. What is the tablet that you use? Is it Gelusil? No? Is it a tablet? Yeah, I heard. What's that? Digene. Oh, yeah, Digene. It's a tablet form, right? So yeah, we call it Tums in the US. Okay. So when you just I'm giving an example. So if you ate a lot, okay, and then if your tummy hurts, so you want immediate relief, right? So then you take, you consume a Digene or want some tablet, right? So Digene or any those kind of tablets will be of high porosity will be very high. So when you consume that tablet, you wanted them to dissolve immediately, right? So you want to get immediate relief, right? But at the same time, if you are having a fever, right? So fever, again, it's a long process, right? So it doesn't go off for like 3-4 days, right? So you want continued supply of drugs, right, or medicine. So those tablets usually come in like very compacted form, right, or in capsules, like very, solid capsules. So that releases nutrients very slowly. Their particle characteristics will be completely different than the particle characteristics that you see in a Gelusil. Okay. So those, again, going back, the particle size, those particle characteristics, we use them to design our products. Okay. So if you take any products, most of the time we use their fundamental properties to adjust their process performance. Okay. Same for fertilizers, or soil, anything. Okay. Fluidization, again, we talked about briefly, right? So fluidization, again, it depends on the density, right? So the relationship between the density and the particle size, their fluidization behavior will also be different. So ideally, we want in this area where we can easily fluidize them, or we can easily convey them using the pneumatic process. Okay. So the particle size, density relation should be, around this area. But if the particles are of very small size, then they will be very cohesive and it will be very difficult to fluidize them. Okay. Or if they are very large in size, then they become spoutable, not fluidizable. Okay. You all know about popcorn, right? How the popcorn machine works. So mostly it's spouted bed rather than a fluidized bed, right? So you might end up with a spoutable bed than a pneumatic conveying system. So compact strength, again, we will talk about tensile strength, etc. But with the increase in particle size, the compact strength goes down. So if you are making any, food powder tablets, like nowadays there have been lots of work going on making, dairy powder compacts, making well mixed dairy powder compacts so that they dissolve quickly. So if you are in the future, if you are going to work in that industry, make sure your particle sizes are small so that they will have good compact strength, so that they won't break during handling process. Okay. Dust explosion, again, if the particle sizes are small, the energy released will be much quicker, and then the explosion severity will be higher too. Okay, if the particle sizes are small. You know, I'm not sure. Any of you working on 3D printing? You are. What are you printing? Which powder? You can sit.
Printing are based on what we can see. We are first we prepare for ink.
Okay.
After that we have to work to done this type of part we have to design on AutoCAD or something like that.
Oh, okay.
After that we have to design.
Okay. Okay. So it's just an example here. You know how particle size. This is printed spinach. I don't know how they are very. I don't know how many of you all know spinach, right? The green leaf vegetables. Okay. Okay. So in this example, you can see. I was thinking, why do someone wanted to print spinach? Okay. Okay. So it's. I know for kids and young people, spinach is not a favorite one, right? It's not a favorite vegetable, right? But so here, again, larger particles had a better shape or better stability. It's not about the shape, better stability for the printed, 3D printed material or spinach than, when they extruded with smaller particles of spinach. Okay. So again, depend on the process, these properties change. Okay. And other effect segregation, definitely, right? If you have a mix of larger and small particle, you will have a big effect on segregation. Even if it's smaller particles too, if it differs in chemical composition, then you might see some difference in the property after handling. That means it segregates a lot. Again, hydrodynamic effect, inertia, etc. Fracture strength too. If in general larger particle will have a more higher chance for fracture initiation sites, or where you will see more stress concentrations that leads to breakage of particles. So again, depend on the size. Okay, so this is again, we will talk about that. In general, again, this slide is from Malman. We use sieve analysis for larger particles and microscopy techniques for smaller particles, right? That's the range commonly we use, but again, we talked about the type of measurements and their physics, right? So again, do you know what principles sieve analysis uses to measure the particle size? So what are we using? What property of the material are we using to get the particle size? Spherical diameter, no, not. What is the property of the material that we are using when you use a sieve analysis to get the size? Not major diameter. So that's again that you both talked about the sieve opening, right? So sieve opening will again major diameter, not always, right? So if the particle is slanted, it can go in any orientation, right? We'll talk about that in a minute. But how do we measure particle size using sieve analysis? What do we do? Can anyone explain? What do we do? What's that?
Volume fraction.
Volume fraction, no, that's in laser diffraction we use volume. Okay, now we are close. Okay, we don't use volume. So what else we use for sieve analysis? What's that? No, very close, not that. What's that? Mass fraction, mass, right? So weight. So based on weight, so particle size is based on the weight, right? So amount of samples that that's collected in each sieve, that's a property that we use to get the size, right? We use we calculate the arithmetic mean diameter from the amount of samples we see, collect in, different sieves. Okay. So that's again, that uses weight. Sedimentation uses again Stokes principle, right? Aerodynamic, property. Yeah, SEC, it's very small particle again. Optical, imaging again for two-dimensional orientations. Laser diffraction again, optical influence, or light influence on particles, right? So we use different principles, But again, the measurement techniques, they all differ on the degree of resolution, right? So if you go, to a high-end instrument, then the degree of resolution will be much better, right, than a sieve analysis. Okay. Again, as we talked about sieve analysis, the particle orientation may not be constant. So you always get a mix of, you take sample from, that's collected in each sieve, you still get a distribution, within that sample. Okay. Again, the principles, that different systems or different techniques uses are not the same, right? That depends on the type of instrument that you used and type of instrument that we use, and the type of distribution that we get are also not the same, right? So there are three different types of distribution that we normally characterize, the size distribution of powders that we characterize from the measurement techniques. Okay, can anyone know? Can anyone give the three distributions that we characterize? Particle size distribution. So at least two of them you gave, but you just have to say them. So volume based distribution. Okay, one is volume based distribution, one is mass based distribution, right? So what is the third? Any guess? Surface area, yeah. So we don't commonly use, yeah, we can use surface area too. What's that?
Surface volume distribution.
Surface?
Surface volume distribution.
Yeah, surface volume, yeah. So that's again surface area, but there is another basic. These are from other properties, right? But volume, weight, and number based distribution are the three common distribution that we use in different measurement techniques. So number based distributions are, if you are using any microscopy technique, we use this number based distribution because the size or the characteristics will depend on the number of particles that you are using to measure, right? Any of you use microscopy technique for measuring size? No? No one? So there is Malvern G3ID that uses optical principle, or you can use any optical microscopes too. Okay, so put some particles in the slide and then you measure the size. Okay, but again, if you increase the number of particles that you are spreading on the slide, then your values will also be different. Okay, so the distribution is based on number. So based on the number of particles we use to characterize, then the distribution will also change. Okay, but for laser diffraction, it uses volume. Okay, but for sieve analysis, it uses weight based distribution. Okay. So again, we'll talk more about those things when we come back in the afternoon, okay, for lunch. First we'll talk about microscopy and then we'll go on to some of the other common techniques. I will not be covering all the techniques, but some of them. Okay. Any questions before you guys leave for lunch? No? Okay.